and Professor Daniel Carando, University of Buenos Aires, Argentina. So please, Dr. Carando, go ahead.
Is my camera on? Yes, it's on. Okay. Well, thank you very much for the presentation. Thank you very much for the invitation. I'm very happy and honored to be part of this seminar.
Thank you.
I will talk about some stuff about Dirichlet series, especially from the point of view of the functional analysis, conversions, questions, and things like that. My idea is that the first part of the talk will be an account, I hope an accessible account to some classical questions, and then in the last part I will talk about some recent research together with Andreas Defant, Felipe Marseca, Ingo Schulman, and Pablo Sevilla Peris. I will talk about that later. But to start in the most elementary way, I will start with a very basic remark on power series, which is the following. When you talk about the radius of convergence of a power series, we never said to which kind of convergence we refer. And that's simply because it doesn't matter, because we know that the same radius of convergence works for pointwise convergence, absolute convergence, and also serves as a limit of the radius for which we have uniform convergence. So we have just one radius, which gives essentially the region of uniform convergence, of the region of absolute convergence, and the region of pointwise convergence. Of course, in the boundary, we can have some difference, but there is essentially one region of convergence for all kinds of convergences. This is a very particular property of power series. If we take Fourier series, it does not happen. The region of absolute convergence or convergence can be very different. And what happens with Dirichlet series, which is the subject of the talk? Well, first, we recall what a Dirichlet series is a function of this form. We have some coefficients, complex coefficients, and 1 over n to the s, where s is the variable. For historical reason, we use s as the variable of a Dirichlet series. And the main difference between a power series and a Dirichlet series is that in the power series, we have the variable to the power of n, and in the Dirichlet series, we have n to the power of minus the variable. Little difference makes a lot of difference when we study convergence of this kind of series. The main difference is that the region of convergence of a Dirichlet series is half planes. The Dirichlet series converges in half planes. That is to the right of vertical lines. And this is very easy to see for absolute convergence, because if you take absolute value here, well, and what you see is that the absolute convergence only depends on the real part of S. And the real part of S is big enough, this series will converge, and if not, it will not converge. So if we take, for example, what is called the abscissa of absolute convergence of a Dirichlet series, which is simply the infimum of the sigma such that this series converges, then it is easy to see that, well, it's almost evident that to the right of this number, if the real part of S is bigger than this number, the series will converge, and if it's smaller than this number, the Dirichlet series will not converge. Absolutely. In what cases, absolutely. Of course, this can be minus infinity or infinity if the series never converges or always converges, but these are extreme cases. So at least for absolute convergence, it's easy to see that the convergence is in half planes. For pointwise convergence, it's not so easy, but you can do it. It's a nice theorem that the convergence also is in half planes. So again, you can consider the abscissa of pointwise convergence, which is the name of the thus this Dirichlet series converges in this half plane. And we have convergence in all these. Now, if you we can again consider the largest half plane in which we have uniform convergence. This means, in fact, that if we take any smaller half, we have uniform convergence here. You must take R smaller than the radius convergence to have uniform convergence. But a priori, since uniform convergence implies convergence, the half plane of uniform convergence will be a priori smaller than the half plane of convergence. And using Weierstrass Majorana test or something like this, we can see that the half plane of absolute convergence is a priori smaller than the one of uniform convergence. You know, the fact that the half plane is smaller is shown because the abscissa is greater. The greater abscissa gives a smaller half plane. So to make a summary of what we said here, we have power series, we have Dirichlet series. For power series, there is one radius of convergence that determines essentially all convergence, pointwise, uniform, and absolute. And for Dirichlet series, we have half planes, and we have a half plane of pointwise, uniform, and absolute convergence, and they, as we will see, may differ. This is two differences. Convergence in half plane may differ. Another question which will be important later, when you rescale the variable in a power series, you rescale the radius. If you multiply divided by 2, the radius decreases in 1/2. What we can do here, since convergence is in half planes, the natural operation here is translations. If we translate as the Dirichlet series, the half planes of convergence will be shifted forward. The exact amount of sigma. So translation will shift the half planes of convergence. But we said here that the half planes may differ depending on the convergence you are considering. Let's see a few examples. First, how do relations of convergence, point-wise convergence, and absolute convergence relate? Well, this is also easy, because if we have that at some S0, the series converges, then if we move 1 plus epsilon to the right, we have absolute convergence. And this is simply because if you take absolute value in the series evaluated in C0 plus epsilon plus 1, then we have these coefficients which go to 0. These are the general term of that converge. We are assuming that series converges at C0. And then since we have n to the 1 plus epsilon, this sum is 5. And this will be, so this says that if you take any point here and move 1 plus epsilon to the left, to the right, we will be in the region of absolute convergence. Since this is for every atom, what it means is that this width is at most 1, because of this. Because each time I move a little more than 1, I go outside the strip. So the strip of convergence, not absolute convergence, is at most, the width of this strip is at most 1. Which is, this is what we said here. And taking this class, right, function, easy to see that for this case, the convergence is in real part of S greater than 0, and absolute convergence is in real part of S greater than 1. So the strip is exactly 1. So this is a very example where the region of convergence absolute conversion is the maximum possible. We have the distribution it has width exactly 1. And we can see that is the use. Now, what does this relate with the translation operator? Well, if you have a single series, we always can define the translation of D by sigma is simply D of S plus sigma, which has this expression, and we can rewrite it this way. It's not important, but we can also always do this. So this can be thought of as an operator that maps D to D sigma, and that's the so-called translation operator that maps some D to D sigma, which is the translation by sigma of D. Now, what we saw just now, that the strip of some where a Dirichlet series can converge, but not absolutely, is at most 1, can be rephrased in terms of the translation operator by saying that, for example, if we fix a half plane, the typical half plane we fix is the right half plane, which is where the real part is at the right of the imaginary axis. This is the natural. Well, what we can say is that for every sigma greater than 1, the operator tau sigma maps a convergent series in this half plane into absolute convergent series in the same half plane. And of course, and one is sharp because we have shown an example for which less than 1 will not work. So this problem of the width of the region where something happens but something does not happen sometimes can be reformulated in terms of this operator maps this family of series into this family of series. And sometimes this is helpful because a problem, the conversing a problem of defining an operator and seeing that this operator is bounded or things like that. Well, but much more interesting, more deeper, and with more consequences was the problem of how do the region of uniform and absolute conversion relate. This is the so-called Bohr's absolute conversion problem, which is to establish the maximum width of the strip where some series converges uniformly but not absolutely. For those who never heard about Harald Bohr, this is Harald Bohr on the left. On the right is Niels Bohr, which will be Nobel Prize in physics some years later. But at this time, Harald was much more famous than Niels, but not because he was studying the Dirichlet series, but because he was a player in the Denmark football national team. This is Harald Bohr. This is the Denmark national team who played in the Olympic Games in London. And he was a very popular member of the national team. He was something that people stopped in the street, not to take selfies because there were not selfies, but they stopped and they were something very, very loved by people. Well, let's go back to mathematics. This is the problem Harald wanted to solve. Which is the maximum width of the region where some Dirichlet series converge uniformly, but not absolutely. And well, this is again the same problem. And so he defined this number, the supremum of these quantities, precise for a fixed D. This is precisely the width of the strip where this series converges uniformly, but not absolutely. It is precisely the width. So we're taking the supremum. It's a maximum here, but eventually will be a maximum. That can be shown. But in fact, we want to the supremum of all the widths of all the region of uniform, but not absolute conversion. The observation is that instead of working with all Dirichlet series, we can fix a region of uniform conversions and only move the absolute conversions. So we can simplify a little problem, thinking of that we take all Dirichlet series that converge uniformly in the right half plane at the right of the imaginary axis, and then take the supremum of the abscissa of absolute convergence of this. We are fixing this is essentially to say that this is 0, so the difference is just sigma A of D. And this is not exactly 0, but this is the idea. Something much deeper, which we usually call the fundamental theorem of Bohr from 1930, was that you can change uniform convergence by boundedness. This is not obvious, but this is a big theorem of Harald Bohr. And why is it important? Because bounded Dirichlet series on a fixed half plane work as they are a Banach space. You have infinity norm. It can be seen that the norm Dirichlet series are complete, bounded Dirichlet series are complete, and so you have all the function analysis to work with. What's more, you can rephrase this in terms of operators. You can say that what we were looking for is the infimum of the sigma, such that the translation operator maps bounded Dirichlet series in the half plane into absolutely convergent Dirichlet series in the half plane. So this is more function analytic way to express to state the problem. But so he made all this reasoning, but maybe but he hadn't so he proved that this S was at most 1/2, but he didn't know if it had to be greater than 0. He really didn't know if there were Dirichlet series for which the convergence, the uniform convergence and absolute convergence have different regions. It was Steplitz who told him, gave him an example of a region of a Dirichlet series with a region of 1/4. So thanks to Steplitz's example, this way, I think it was the same year of 1915, but almost 20 years later, when Banach spaces were already invented, Borenblus and Hille were able to show that this width is exactly 1/2. So, and they even show that this supremum is a maximum. They showed an example of Dirichlet series for which the strip of uniform but not absolute conversion is exactly 1/2. That's why we say here the maximum width is really a maximum. Well, but Bohr, when he was thinking about this problem, found out something which is curious or interesting, is that if instead of an arbitrary Dirichlet series, we take a Dirichlet series but which only consider prime numbers, the only n which has an different from 0 are prime numbers. So you have 2 to the s, 3 to the s, 5 to the s, 7 to the s, and so on. Pk is the kth prime number. Then the relation of uniform conversion and absolute conversion are exactly the same. So if you restrict to this kind of series, the width is always 0. The width of the strip is always 0 because the region is exactly the same. And before we give an idea of why this happened, not a proof because it wouldn't be too long, what is the main difference between an arbitrary Dirichlet series and the Dirichlet series? What? Sorry? Okay.
There is no comment. Please go ahead.
Okay. No problem. So the question will be, which is the essential difference between an arbitrary Dirichlet series and a Dirichlet series which is supported only on prime numbers? Well, if we write them, the series as an exponential sum, we think of this like frequencies when we write this as exponential sums. What we can see is that these frequencies, in the case of prime numbers, are Q linearly independent. These are linearly dependent over Q. Well, these are not, clearly not, because, for example, log of 2 plus log of 3 is log of 6. So this shows that these are not linearly dependent. But it is easy to see that these are Q-linearly independent using the fundamental theorem of arithmetics, the uniqueness of expansion in Prague numbers, and so on. So this is a difference we find between these two cases. Like, the question is why Q-linear independence has to do with problems of convergence. And let me give an idea. Suppose that we have a series that converges in the right half plane, at the right of the imaginary axis. Then, since the partial sums are uniformly Cauchy, we can make this sum as small as we want, as arbitrarily small. Now, using in a very clever way, the maximum modulo principle, we can see that the supremum of this expression in all the half plane is the same as the supremum in the imaginary axis. This is not a direct use of maximum modulo principle because we don't have a maximum here. These are supremums. We're not in a compact set where we can use maximum principle, but with some clever ideas, we can show that this supremum and these supremums are the same. This is because this is a very particular holomorphic function. It's not any holomorphic function. So now what we do is to write this sum as an exponential sum. And now we use the fact that these frequencies are Q-linear independent because Kronecker, a classical result of Kronecker, showed that that this curve in the n-dimensional torus, this is like a curve inside this in the n-dimensional torus in the complex space, in the CM. This curve is dense. In fact, it's more than dense, it's ergodic. That means that not only the trajectory are dense, but they cover uniformly the torus in some sense. But no, we don't need to understand. But for those who know some ergodic theory, this flow, this Kronecker flow, is ergodic in the torus. But we only need density here because we know that the supremum over a dense set, we are taking a function on these elements, is the same as the supremum over the whole set. So this supremum is the same as taking all C1, Zn in the torus and taking the supremum of all this. And once we have this, it's easy. We can take, for example, Zj, Ck to be the sign of Bk, and this sum gives simply the sum of the absolute value of Bk. We have always this because triangular inequality, and we have the equality because you can take Ck to be the sign of Bk. Now, we said that this could be made as small as we want. We can take this small, an epsilon, taking m and n big enough because of the uniform convergence. But then these are all equalities, so we can make this sum arbitrarily small, taking m and n sufficiently large. And this is exactly the same as saying that the series converges uniformly in this region. Because, just a comment, 1 over s, this is always 1 over n to the s is always smaller than 1 if real part of s is greater than 0. So we can put now 1 over n to the s, and if this is smaller than epsilon, with this always will also be smaller than epsilon. So after this observation, after many other observations of the people realized that this kind of series were interesting to be studied in terms, and to study properties of this series in terms of properties of these numbers, which we will call frequencies. And that's why at the beginning of the first decades of the last century, many authors, many mathematicians, Rees, Hardy, Landau, Bohr, and many others, studied what now we call general Dirichlet series, which are exponential sums with some frequencies, which are positive real number increasing to plus infinity. And of course, when we take lambda n to be log n, we have the ordinary Dirichlet series. And just to get another example, if we take lambda n to be n, we have this expression that if you take S to be IT, we obtain a Fourier series. And if we make this change of variable, we call z to this e to the power of minus s, we have a power series. So in some sense, this theory was appealing because it comprises many well-established and interesting theories. You have in the same framework, Dirichlet series, Fourier series, power series, and different another interesting situations. Well, so we are now working with this kind of Dirichlet series, general Dirichlet series, and let us first define the simplest space of Dirichlet series we can define from the function analytic point of view, which is taking all the Dirichlet series, we fix a frequency, and we consider all the Dirichlet series for which the coefficients are two summables. The coefficients are in L2. This is clearly a Hilbert space. And the problem now will be to understand, now that we have all the series in this space, we want to find a common domain for all these series. So we can do many things with this, but let us focus on one which is simpler to understand. We want to understand which is the region of absolute convergence of H2 lambda. That means which is the half plane in which all series in H2 lambda converge. And it is interesting that this half plane has to do with how our new frequencies behave in terms of the classical frequencies, which are log n, we give the ordinary Dirichlet series. Because Andreas Deff and Nico Schulman from Oldenburg, Germany, showed that the largest half plane in which every series here converges in this converges is precisely is to take L of lambda over 2 and go at the right side. This is the largest half plane in which every Dirichlet series here converges. Of course, if you take lambda n to be log n over log n is 1, so we have this half plane. This was known. This for ordinary Dirichlet series, this space H2 was defined by Hedelman, Lindquist, and Seip, and probably one of the I think probably the most influential article on the subject, which was almost in 1998. All the new theory about Dirichlet series from the analytic point of view, and many of the results of this subject are consequences of this great article. Of course, Helson also worked in this space for log n, and many others. It was a very studied space, the H2 for ordinary Dirichlet series. But we want to define Hardy spaces HP lambda for P different from 2. And first, let's go back to P equal 2. We know that if you take as finite sum, the norm of this finite sum in H2 will be the sum of the coefficient to the square and 1 over 2. When we define the P version of a space of functions, in general, we don't put in the coefficients P. We want something more, some integral, which in this case has exponent 2, well, to put an exponent P. LP of 0, 1 is not to take Fourier series with coefficient summing to the p. Is that the integral to the p is finite. So fortunately, we have an integral representation for this norm, which has to do with ergodic theory. It doesn't matter the formula you don't have to look very carefully, but the good idea, the good news is that we have an integral to the power of 2 that gives the H2 norm. So the natural way to define now and it's natural in many senses. We will not get into details, but it's natural in many different ways. Is to take precisely the same expression but putting p instead of 2. This is a norm. This has sense. This limit always exists thanks to ergodic theory, and we can define HP lambda as the completion of Dirichlet polynomials. Dirichlet polynomials are these finite sums with this p norm. We cannot put here infinity because this makes no sense. But if we complete the space of Dirichlet polynomial with this norm, we obtain a space of Dirichlet series. This was shown by Bayard for ordinary Dirichlet series in 2002. And by Defan and Schulman in 2020 for general Dirichlet series. Okay, we can forget about these expressions. We only have to remember that we have HPs, which are spaces of Dirichlet series, which in some sense resemble LP. They have a P norm which resembles the P norm of LP of the 0, 1, for example. Now, we want to understand now which is the largest half-plane in which every series here converges absolutely. So we can do something similar to what Borg says did. We can define SP lambda as the supremum of the abscissas of absolute convergence of all the Dirichlet series in HP lambda. And this will be the best abscissa that works for every series. We take each series and then take supremum over all series. And again, we can reformulate this as the infimum of the sigmas such that the translation operator maps HP lambda into absolute convergent Dirichlet series on real part of S greater than 0. So we can think any of this. For example, the result we mentioned before that for H2 lambda we have this is the largest half-plane. This is equivalent with this notation as S2 lambda is L of lambda over 2. And again, for ordinary Dirichlet series, this was solved by Bayard. Bayard showed that all SP lambdas, when we take these frequencies, are all equal to L2, to 1/2. This was very surprising when he obtained this result because HP lambda, HP when we do not put lambda is because we are using the ordinary case, the log n. All the HP are different. They're really different. They're contained, but you have things in H1 which are not in H2, things in H2 which are not in H3, and so on. But no matter that, all these spaces have the same half-plane of absolute convergence. But that was surprising when Bayard obtained this result. Well, so this is our citation. We want to determine SP lambda when we have an arbitrary frequency, and again, this value is very related with many questions on Dirichlet series. It was very natural to. I think Landau was who first defined this value. I think the L is for him. I'm not sure, but I think it was. But well, again, the half-plane of absolute convergence for all functions in HP will be related to this L of lambda. And what you obtain with Andreas Stefan of Oldenburg, Germany, Felipe Marseca, he's from Argentina, but now he's in London, in King College. Ingo Schulman from Oldenburg also, and Pablo Sevilla Peris from Valencia, in Spain. We obtained that for p greater than 2, we have the same situation as in the ordinary case. All the SP lambdas, all the half planes of absolute convergence are exactly the same. It doesn't matter if the HPs are not the same, the half plane are all the same. And for p between 1 and 2, we have this lower and upper bound, this estimate on the abscissa of absolute conversion that works for all series in HP. Bayard showed that for lambda log n, in fact, we have equality in the lower bound. And in fact, there are many other situations where we have equality in the lower bound. For example, if the frequencies are Q-linearly independent, again, Q-linear independence has to do with this kind of problems of convergence. Something rather weaker, something weaker than linear independent is to be B2. To be B2 means that the sums of any two elements, any two frequencies are all different. The only way that have the same sum between two pairs of frequencies is that, in fact, it was the same pair, maybe with a permutation. This is Q-linear independent frequencies clearly satisfy this, but this is much weaker than Q-linear independent. And if we allow repetition, this means there is no repetition when you sum. If we allow repetition, but not excessive repetition, it doesn't matter. This means that the number of repetitions increase sub-exponentially on the sum. It doesn't matter. Again, for this case, we also have that all SPs are equal to L lambda over 2. And I mention this because log n, lambda n equal log n, satisfy this property. And so this recovers in a much more complicated way the Bayard's result that said that for log n, all the SPs were the same. Well, so the situation now is, just a comment. Why is this important? Why we have this repetition of sums? To control the repetition of sum is important. It has something to do with the problem of studying this kind of series. This is not a justification. It is simply an idea, a hint of what's going on there. Just very, very simply, if we take an exponential sum and to the power of 2, the square of an exponential sum, well, we expand it and we have something like this. Of course, we have to be carefully for conversion, but forget about it. If we want to write this sum as a new exponential sum, we must to regroup all the terms that have exactly the same frequency here. So if a lot of different pairs give the same frequency, the regrouping will be uncontrolled, and this is complicated. If the number of pairs that give the same sum is controlled, then it is not difficult to rearrange them, to compute things, and for those situations, you can compute the abscissas of absolute convergence and give what we expect to give, that is the lower bound. So this is not a justification. This is just how these sums appear, how the repetition of sums appears in the question. So let's go back. We know that for p greater than 2, this is always L lambda over 2, and we have this bound. And for many frequencies, we have equality here. So the natural question was if we have sometimes equality in the upper bound. And Bayard, in a recent article in Channel, a very deep article, this is just a little part of the article, he showed that there exists a frequency for which for p equal to 1, he has equality for the lower bound, for the upper bound. One works, we have equality there. And the construction is very clever. I will not detail, but we know that when we have few repeated sums, then we have equality in the lower bound, what we mentioned before. So we need lambda to have many repeated sums. And many repeated sums are the frequency which have more repeated sum are arithmetic progression. And arithmetic progression, there are a lot of repetition. But arithmetic progression have L equal to 0 because they increase linearly, so logarithm over lambda n will tend to 0. And with 0, it's obvious that everything is 0. It's not fun. So we wanted some L which is not 0 nor infinity for this to make sense. And what Bayard did is to choose in each interval of length n, of length 1, an arithmetic progression of size 2 to the n, and then he put them together. But they had to be chosen very carefully. I put well here, but in fact it's very subtle. It's not easy at all. But he made a very clever selection of this arithmetic progression, and for this combined, he had an example where this happened. So let's update the situation. P greater than 2 is always the same, so it doesn't matter anymore. Now, for P smaller than 2, we have that SP can be is always between these two bounds. We sometimes have equality for the lower bound, and for P equal to 1, there is situations when you have equality here. Well, there are two, I think, natural questions now. The first is if we can do the same as Frederic Bayard in other P's. If we can have equality in the upper bound for P's different from 1. This is one of the reasons. And then if we can do this, what happens with the intermediate values? Can I have a lambda for which this gives the average of these two numbers? Well, so we'll recall two things. For Q linearly dependent, we had equality in the lower bound, and the glued arithmetic progression, the Bayard's frequency, give equality in the upper bound for P equal to 1. So what we did with Felipe, Andreas, Pablo, and Ingo was to mix two linearly independent frequencies and Bayard frequencies, or something similar to Bayard frequencies, and dosify how much collinearly independent frequency and how much glued arithmetic progression you put, and then show that we can obtain anything we want. For any P, for any eta between P and 2, we can have a frequency that has SP lambda equal to L lambda over eta. If eta is equal to P, this gives the equality in the upper bound, and if we have other etas, we have all the intermediate values between L lambda over 2 and L lambda over P. So this, in some sense, solves the problem of convergence for HP lambdas, the region of absolute convergence for HP lambdas. Of course, is probably the deeper idea. The deepest idea is that of the Bayard to build this frequency. But this is not easy. I think that this conclusion is very interesting because it was not so easy how to dosify these two things. And taking the union of frequencies may sometimes not always is easy to know what happens when you join two frequencies in a new frequency. Well, but let's go back to translations. Again, given now a general Dirichlet series, we can consider the translation here, which is simply to add sigma to the variable. we have this expression, and again, we can have an alternative expression for this. And again, we can think this as an operator which is applied to D. Tau sigma of D is exactly D sigma. Well, Bayard in 2002 for lambda n equal log n showed that the operator tau sigma is always well-defined and constructive between the HP spaces, and Defan and Schulman showed this for arbitrary lambdas. That means that if I could take a Dirichlet series in HP lambda, then all the translation, positive translation, will remain in HP lambda. And well, since HP is contained in HQ if Q is smaller than P, then tau sigma will be also constructive for any Q smaller than P, from HP to HQ. And it's a natural question, what happens if Q is bigger than P? So a result we have with Andreas, Felipe, Ingo, and Pablo is that if we take P between 1 and 2, and we take Q greater than P, then if we want the translation to be well-defined and continuous from HP lambda to HQ lambda, we need to take sigma greater than this value, where again, L of lambda appears. This result is sharp in the sense that if we want sigma which works for any frequency, then we have to take this. Something smaller than this will not work. But for certain lambdas, we can have better. So again, if we take particular lambdas, we can do better. And this is an extreme case is the so-called hypercontractive frequencies that are we will define now, which is the frequencies for which all the translation operator are well-defined and continuous for any HP into any HQ, no matter which is greater, which is smaller, which is bigger. This is it's hard to understand why this should happen until you work on these things. Just a comment: any hypercontractive frequency will satisfy this, and then the Bayard's frequency, he built his frequency to show that he was not thinking about this problem. He was thinking about to find frequencies which are not hypercontractive. And then Bayard, since Bayard satisfied this, since Bayard's frequency satisfies this, then Bayard's frequencies is not hypercontractive. Well, Bayard in the article, in the same article in which he built this his frequency, showed that if this limit is 0, that doesn't matter. But now we'll take a look at this. Then the translation operator is bounded, well-defined and bounded from H2 to H2K. Here we have Q, which is greater than P. If this is P, so this is the non-obvious case. So he said that if we have this condition, then we have not for every P, every Q, but for 2 to K. And again, this has to do with the repetitions of the sum. This means that now if we take K frequencies and sum up them, we don't want that this sum, the result of the sum, repeat too much. And again, if log of this is bounded by mu, then we want a sub-exponential control of the repetitions in the sum of K frequencies at a time. Well, the interesting part here is that this condition that seems weaker than being hypercontractive, because we don't have every pair here. For example, P cannot be 1 in this situation. we show that, in fact, this is enough to ensure hypercontractivity. So this is, again, in our work with Andreas, Felipe, Ingo, and Pablo. And then this allowed us to restrict to attention. In order to characterize hypercontractivity, we only need to consider these kind of things. And this motivated us to think that the question had to do with the repetitions of sums of k elements at a time. So there is something that people working on additive combinatorics uses is the additive energy of a set. The k additive energy is precisely the number of repetitions you have each when we sum k elements of your set. They don't need to be different. So if you set is an arithmetic progression, this makes sense for finite sets. If your set has a finite is an arithmetic progression, then the kth energy is maximum. If you have a Q linear independent, the energy is minimum, and you have everything in between. So this is a very not useful tool in additive combinatorics. Well, what we saw is that this is our main theorem, is that if you have this growth condition of lambda, then hypercontractivity is equivalent to this limit going to 0. Don't worry very much. Again, it has to do that here we are taking elements of the frequency which lie between j and j plus 1. The problem is, again, that we need that the number of repetition will be controlled, should be controlled. Don't worry about the exact expression. This is, again, the same idea of always. And just to finish, why this energy has to do with what we do. Remember that we said that hypercontractivity had to do with H2K. The theorem said if from H2 to H2K is bounded, then it's hypercontractive. When we compute the H2K norm of a Dirichlet series, it's a trick. We can rewrite it as the 2 norm of the series to the power of k. This is something very simple. When you expand this, we obtain this expansion. And again, you have to regroup these things in terms of how many of them are repeated. If you do that, what we finally obtain is the energy, the kth energy of the set A. So this here is in fact almost the norm of this Dirichlet series. And this here is the 2 norm. This is the 2 norm to the square of the same, because the 2 norm is to sum 1, 1, 1, 1, and then taken to square root. So we have the 2 norm of this series is this here. The 2k norm here is this here. So this has to do with the relationship between 2k norm and 2 norm. But also, it turns out to be the kth energy of the set A. Well, this is all. Thank you very much for your attention.
Thank you very much for the beautiful talk. So now it's time for questions, please, if there are questions. Meanwhile, may I ask you first, if there are generalizations of these results onto quaternionic analysis case or Clifford analysis? So instead of complex numbers, quaternions or Clifford numbers.
I really don't know. It would be interesting, I think, because this kind of, we call them general Dirichlet series, but they are exponential sums and they appear a lot of situations. So I confess I don't know, but I think I will look up for it because maybe there are still, maybe there are similar things that they not do the same, so you don't realize that. But since this kind of exponential sums and this ergodic average to compute norms are very appear in many situations, so I think it could be possible. Yes. That would be interesting.
Thank you. More questions, please, comments? So it's still time to comment. Everything was
okay.
clear.
or maybe let's hope so, but
okay. I think there are no questions, so thank you very much again. It was really very interesting talk. Thank you, and thank you for accepting our invitation here.